Okay, yeah. So you can look at this review is the last page of the last our last class, so you can take a look at that, or second to the last page, because we went into a little tangent on an application where we were looking at the page rank system or algorithm. So yeah, let's do some examples. I have some examples over here. Which one? I guess we'll go in order. Here's a couple of questions. Oh, one more thing about being diagonalizable. Let's go back to here. An important feature of a diagonalizable matrix. Or a diagonalizable. If you have a diagonalizable matrix, then that means we should be able to write A is equal to P, D, P inverse, where D is some diagonal matrix and P is some invertible matrix. What happens is that, I don't know if I showed this to you guys before, but if you raise the matrix to a power, we would get P, D, P inverse times P, D, P inverse. So that's what A is equal to, right? And although the matrix multiplication is not commutative, it's associative, which means we can regroup any way we want. So if we take a look at regrouping the two middle terms, the P inverse times P, and that's just the identity. So to be really formal about this, we would write P, D, P inverse P, put that in parentheses, and then that would be the identity. And then the identity is just itself, so it'll just be D squared in the middle. Okay? And I don't know if you noticed, but when you square a diagonal matrix, it's really just squaring its diagonals. So in other words, if I have 3, 0, 0, 5, and I square that, that's 3, 0, 0, 5 times 3, 0, 0, 5. And that's just going to be 3 times 3, 0, 0, and then 5 times 5. So squaring it is not that big of a deal, but if you take it to some randomly arbitrary high number, a whole number, then you can say a to the k is going to be equal to P, D, P inverse, and then a whole bunch of them. So there's k of these things. And then what happens is that there's going to be P inverse times P that's going to cancel out throughout in the middle. And then you should work out A to the third, A to the fourth, A to the fifth, so you can convince yourself that this is actually true. But this will reduce to A, D to the K, P inverse. So if you're raising it to the 20th power or something like that, then instead of multiplying A 20 times by itself, which could get kind of difficult, you can just take each of the diagonals, raise it to the 20th power, and then the only matrix multiplication you have to do is the P times P inverse, the P on the left side and then P inverse on the right side. Okay, so this is another advantage of being able to use diagonal matrices, is that if you're going to square it or take it to the third power, to the fourth power, to some higher power, then the diagonals are just going to be whatever the diagonals to that powers are. And then you just multiply by P inverse on the left, and then the result, or P inverse on the P on the right, and then P inverse on the left. Or backwards, whatever. You know what I mean? All right, so let's go back to this example that we were looking at. And Let's do some warm-up examples. So here they gave us, we don't have to go through the process, although we probably, well, we don't have A, so I guess it doesn't matter. Here they gave us what A is equal to already. So they want us to compute A to the K. So I don't know what A is, but I know that A is equal to P D P inverse. And so I think I'm going to eventually, well, let's see, A to the K is equal to P D to the K P inverse. So I think I might be interested in trying to figure out what P inverse is. I think that's probably going to be the hardest part. Well, and then we have to multiply this out, but it's still going to be generally the hardest part of the problem is finding P inverse. Yeah. Well, then that wouldn't be a problem that we would do. It would just multiply the matrix a bunch of times. So the whole point in doing this is because it's diagonalizable. If it's not diagonalizable, then we'd be doing a different problem. Okay, so P inverse, is that easy? I don't know. Let's, oh yeah, this is a 2 by 2, right? So P inverse should be easy. So P inverse is the 1 over the determinant, and then you, what is it? Switch the diagonals and negative the wings. And so what was that determinant? 10. So 1 over 19 times that. Okay. All right. So that's our P inverse. That looks pretty nice. So if we're going to raise this to the K power, that means we're really only going to worry about the diagonals. So our P is 2 minus 3 minus 3, 5. And our D to the K power is 1 to the K power times 1/2 to the K power. So 1 to the K power is just 1. And 1/2 to the K power is just going to be 1 over 2 to the K, whatever that'll turn up. And then our inverse we found to be 5, 3, 3, 2. So yeah, if you just consider that 1 to the K as 1, and then this is 1 over 2 to the K, just to write it a little bit simpler. Then we could do our matrix multiplication. So when we do our matrix multiplication for the first one, it's the row times a column. So we're going to do this first. That's just going to be 2 times 1 plus 0. And then we have 0 minus 3 over 2 to the K. Wait, that's the next one, right? And then we have negative 3 and then 5 over 2 to the K. Okay. And then we'll do one more matrix multiplication here, and that's going to be 10 minus 9 over 2 to the K, and then 6 minus 6 over 2 to the K, and then negative 15 plus 15 over 2 to the K, and then negative 9 plus 10 over 2 to the k. So looks a little messy, but this is the result. We just got some stuff with it says 2 to the k in it. And then whatever k is equal to, if k was equal to 5, then we just put k is equal to 5 and simplify it as we need to. Okay? Any questions? All right, so that takes advantage of this diagonalized matrix when we're doing the multiplication. So the next couple of problems are the actual diagonalization problems. So I'm going to have you try it out for a couple of minutes before I work it out myself. So let's try out problem number 9. So diagonalize this if it's possible. And remember the steps for diagonalization. Step 1, find the eigenvalues. Step 2, find the eigenvectors. Step 3, make up your P using the eigenvectors. And then step 4, write your diagonal using your eigenvalues. So a couple minutes on this and see what you get. Resume. I think this is a good example because it kind of will show us some information also about discrepancies between the algebraic multiplicity and the geometric multiplicity. I know we didn't really define those properly, but let's take a look at what we get here. So to find eigenvalues, we subtract it from lambda times the identity matrix, right? So we want essentially the characteristic polynomial is going to be a minus lambda I, the determinant of that. So we got 3 minus lambda times 1, negative 1 plus 0 or minus 0, 1 minus 0, and 5 minus lambda times 1. So the determinant of this is 3 minus lambda, 5 minus lambda, minus, and then 1 times negative 1. So what do we have here? This is 15, 8 lambda plus lambda squared plus 1. Let's try that again. So lambda squared minus 8 lambda minus plus, right, plus 16. And we want to know when this is equal to 0. And it looks like we can factor this. This is lambda minus 4. So it's a perfect square, which means that we have lambda is equal to 4. It has multiplicity 2. So we'll call this an algebraic multiplicity. Now, the ideal situation is that we would match the dimension of the eigenspace for lambda is equal to 4. So if we do lambda is equal to 4, and for some reason we get 2 eigenvectors, then that would be great. So let's see. Step 2, find this is the E values. We want the E vectors. And to find the eigenvector, we're going to do it for each eigenvalue. In this case, we only have one eigenvalue. And then we're going to put that back into the matrix and find the null space of this matrix. So 3 minus lambda, negative 1, 1, and then 5 minus lambda. We want to find the null space of this matrix. And remember, to find the null space, we row reduce and do everything to try to figure out what the solutions are, assuming this is a homogeneous differential equation or homogeneous system of equations. What's 3 minus? This is -1, -1, 1. 5 minus 1 is 1. So we'd expect at least one solution for this. And we can get rid of the whole bottom row. And that means x2 is a free variable. And then x1 is equal to negative x2 if we bring that on the other side. And so we have x, our solution is going to be x2 and then -1 for the top. And it looks like we only have one. We only have a one-dimensional eigenspace. This is sometimes called the geometric multiplicity to describe the dimension of the eigenspace. So lambda is equal to 4 has geometric multiplicity of 1. And geometric and algebraic multiplicity should match up if this thing was to be diagonalizable, but they don't match up. So this has algebraic multiplicity 2, geometric multiplicity of 1, so this is not diagonalizable. Okay, it's not diagonalizable, then there's not much more we can do about this, so we can't well, we can't diagonalize it. Okay, any questions? Yeah. Oh, because some of the theorem, or one of the theorems that we're looking at, number 7, talked about the matching eigenspaces. So matrix A is diagonalizable if and only if the sum of the dimensions of the eigenspaces equals n. So we only had one eigenvector, 4, and the eigenspace for that is only one-dimensional. Yeah, because it's a line, and the null space that we found only had one vector. So because it only had one vector, it means it didn't match the number, the dimension, the number of columns we have, or the dimension of the matrix, and so we just have to say it's not diagonalizable. Okay. Any other questions? All right. Now for 2 by 2 matrices, if you have algebraic multiplicity of 2, then there's a chance that there's probably very little chance that you're going to have geometric multiplicity of 2 that would match. But you'll see for 3 by 3 matrices that could happen. You could have an algebraic multiplicity of 2, and then the geometric multiplicity would actually match. There's some examples. I don't know if the next example is like that, but the next example that we have is 3 by 3 matrix that you're going to try to diagonalize, and it should be diagonalizable. So spend another couple of minutes. Now this is a 3 by 3 matrix, so it'll be a little bit more challenging trying to find the eigenvalues and eigenvectors, but just go ahead and get a head start on this and see what happens. kind of doing this multiplication here. I don't know if you guys have found the eigenvalues yet, but I'm kind of on my way, and I'm hoping I'm not making any algebraic mistakes. Doesn't look good. You guys get something like this for your characteristic polynomial? No? Yeah? Well, but let's try to see if it's right. So does this look okay? The what? Before this? Minus 18. Yeah. Where's 24? This one? Oh. So is that 6? Is this 11? Is lambda equal 1 a solution? So 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 if lambda equals 1 is a solution, then we could do like the factoring or synthetic division or whatever. So we can assume that if lambda is equal to 1 a solution, then we can divide. I'm going to do long division because I don't remember synthetic division. Minus lambda cubed plus 6 lambda squared minus 11 lambda plus 6. So this should divide out evenly. I think, what do we do? Negative lambda squared. That would be negative lambda cubed here minus negative is positive lambda squared. Subtract. So this would be a minus. You got 6 minus 1 is 5. Bring down the 11 lambda. I probably need to move this over, but this would be 5 lambda. 5 lambda squared minus 5 lambda. Subtract. And this would become a negative 6 lambda plus 6. Bring down the 6. So that would be negative 6. Negative 6 lambda plus 6. And that's a perfect division. So this is going to be my factoring, my first factoring, lambda minus 1, and then you got negative lambda squared plus 5 lambda minus 6. This negative is kind of bothering me, so we could just move that outside and see if we can factor this. With the signs changed now, This is positive, so it means it has the same sign. Two numbers that add up to 5 and multiply to 6 is 2 and 3. So lambda minus 1, this would be lambda minus 2, lambda minus 3. So we have ourselves 3 distinct roots. So we have 3 distinct eigenvalues. So let's find out the eigenvector for each one of those. So that was step 1. Let's go to step 2, where we're going to try to find the eigenvectors for each of them. And so we'll have to do that one by one. So the eigenvectors, I basically want this equation, except I'll replace lambda with whatever eigenvalue or I'm looking at. So let's take the eigenvalue 1 first. Let's call that lambda 1. And then I'm going to need to look at this again. So that's minus 1, minus 1. So I need the null space for this vector. So minus 1 minus lambda. Four, negative 2. Got negative 3. 4 minus lambda, 0. And then negative 3, 1. And then 3 minus lambda. So I'm going to get negative 2, 4, negative 2, negative 3, 3 and 0, negative 3, 1 and 2. Let's see. Let's multiply the top by negative 1/2. So I have a positive 1, negative 2, positive 1. So this will help us get rid of or do the row reduction. So let's multiply the first row by 3 and add it to the second row. I guess we're going to do the same thing. Multiply the first row by 3 and add it to the third row. So this will give us 0. First row by 3, that's negative 6. Add it to the third row, that's negative 3. And then 3. So we'll do the same thing. This is 0, negative 3, negative 6 plus 1, thank you, negative 5. And then 3 plus 1 is positive 5. I was kind of hoping that would be negative also. Yeah. Yes. There you go. That's better. So we do whatever we do to get rid of, multiply by, I don't know, 5/3 or 3/5 or something. So you essentially have a row of zeros in the bottom. So this is going to give us a free variable at x3. So there's only one free variable, so this is going to be a one-dimensional eigenspace. That means x2 is going to be x3, and then x1 is going to be, let's see, 2x2 minus x3. But x2 is equal to x3, so this is going to be just x3 again. So we're going to have an eigenvector of 1. This is 1, and this is 1. Okay. All right, so we'll check um, the second eigenvalue. Our matrix is going to be -1, -2, 4, -2, -3, 4, -2, 0, -3, 1, and then 3, -2. So what's this turn out to be? -3, 4, -2, -3, 2, 0, -3, 1, 1. Let's see if we can just knock out this multiply first row by -1, add it to the second row, and we'll do the same thing, multiply -1 times the first row and add it to the third row. So we have -3, 4, -2. This is 0, -2, +2. And this is going to be 0, -3, +3. So again, that whole thing, denominator stuff will get knocked out. So I get 3, -3, 4, -2, 0, -2, 2, 0, 0, 0. So again, we have one free variable, which means our eigenspace is going to be dimension 1. And we have x2 is equal to x3 again. X3 this time is going to be a little bit more complicated. Let's see. What? Oh, the next one. Sorry. So -3, this would be -4 x2 minus +2 x3. And then x2 is equal to x3, so that would just be so -3x1 is equal to -2x3. So x1 is going to be 2/3 x3. Now, because again we're trying to make this look a little bit nicer for us, your x technically would look like this. It would be 2/3 and 1 and 1, right? Times x3. 233. If you change just another parameter, replace x3 with another parameter, so that's like 3 times x3 or something, then you can just use this as your eigenvector. So we'll say v2 is equal to 2, 3, 3. Now, we go through the same process to find lambda 3, but I think at this point I'm just going to does anybody know what the answer is? 1, 4, 1/4, 3/4, and 1. So let's write that in a scaled version. So V3 is equal to, multiply everything by 4, 1, 3, 4. So geometric multiplicity is 1 for all these, and they have the same algebraic multiplicity, so which is good. Then we're hoping that, first of all, we don't have three different eigenvectors, because something would be weird. So if we have one eigenvector, multiplicity 1, and then another eigenvector with multiplicity 2, then we would hope that that eigenvector multiplicity 2 would have a two-dimensional eigenspace, which means we would have 2 rows of zeros, and then they have 2 free variables, so they would have, the null space would be spanned by 2 vectors. All right, so now that was step 2. We can fit step 3. I'm out of space here. We don't have to. So if we write this in order of eigenvectors, our it doesn't matter, but yeah, generally we want to write it in increasing order. We don't really need to do that, because we just have to match the eigenvalues and eigenvectors. So, but in general, I think it's good practice to write it in increasing order. So our V1 was 1, 1, 1, our V2 was 2, 3, 3, and our V3 was 1, 3, 4. And then our diagonalized matrix, if we write this in order, is 1, 2, 3. So if we find the inverse of P, multiply P times D times P inverse, then we should get the original matrix A. So this was in fact diagonalizable, and this is step 2, step 3, step 3, and step 4. I think in an exam situation, you'll probably have about half of this figured out for you. Maybe I'll give the eigenvalues already, and then you find the eigenvectors. So a good question, something that you probably should try to practice on, would be an example where you have, I give you the eigenvalues, and one of the eigenvalues has multiplicity 2, and you figure out whether your null space is going to be 2-dimensional or 1-dimensional. And if it's 2-dimensional, then yes, it's diagonalizable. If it's 1-dimensional, then it's not diagonalizable. So something like that, where some of the problem would be done for you. It wouldn't be all from scratch like this. Yeah. Yeah. Okay. All right. So I have another one here. Let's just skip through that. Chapter, or the next section, 5.4, really just lays out a relationship between the whole idea of diagonalization and transformation. And the drawings that they have in the book would probably help. So I encourage you to take a look at that. Yeah. In the diagonal, yeah. But the order of the eigenvalues has to match the order of your P matrix, your eigenvectors. So in other words, had I put 3, 2, 1, I would have switched the first and the third columns. Yes. And then lambda 1, lambda 2, lambda 3. All right. Let's see what all this stuff says and what they mean. V is an n-dimensional vector space, and W is an m-dimensional vector space. So this is going back to the idea of a general vector space. And then T is a linear transformation from V to W. To associate the matrix T, we choose an ordered basis B and C for V and W respectively. So this is in general terms right now. So if X is any vector in V, then the coordinate vector X with the B on the outside is a coordinate vector. Its image is going to be T of X in the different basis C. Is that making sense so far? So this is a drawing that they have. It's a pretty good drawing. We're looking at a try to draw this in different colors, see if we can match up our V and then our W, and there's a linear transformation T here. And what they're saying is that if you have a vector X and V, then the coordinate vector XB in Rn is going to be in Rn. So V is in Rn. And so we transform this into a different matrix in Rn. So your X matrix here, or your X vector here, will become this X sub B, which is going to be in Rn. And then there is a corresponding image over here where the image is going to be of T of X. It gets brought down there. So the matrix M that they're talking about here is a matrix that's relative to T that transforms this matrix from one space here in Rn to another space here in Rm. Well, before we do an example, let's talk about this whole idea of diagonalization that we're doing. And the idea in the diagonalization is kind of a change in basis of sorts. So just hold on to this picture for a minute, and then I'm going to try to redraw the picture where the M and the N are going to be the same space, and that will make our relationship to what we're talking about here a little bit clearer with the diagonalization. So let's pull out this information over here. Let's suppose A is going to be diagonalizable, where D is your diagonal matrix, and then P and P inverse are those invertible matrices that are made up of the eigenvectors. And then if B is a basis formed from the columns of P, then D is a B matrix for the transformation A going to AX. All right, so let's see if this makes this picture a little bit clearer. Um, you have the matrix, you have the vector x here that you're going to send to vector ax. Let's call it ax. So instead of going directly to this, the transformation, what happens in a transformation situation is that what you're doing is you have A is equal to P D P inverse. And what happens when you apply this to x is you have AX is equal to P D P inverse of x, right? And remember that when you apply a vector to a matrix, it's essentially matrix multiplication. So what's actually happening here? What's actually happening is that we can consider this P inverse of x. So this is the P inverse matrix that sends this into another matrix that's going to be essentially a changing of basis matrix. And then you're going to send that matrix after you apply P inverse to it through the matrix D at the diagonal. And this is supposed to be the easy part over here because D is a diagonal matrix. And that's going to get sent to this. Now, this is D of X of B. And then when you apply the last part to it, and that's the matrix P, to that, you're going to get back to that original matrix A. So what they're saying here is that this matrix, the matrix D, sends your transformed matrix to another basis to this new vector in the same set of bases, and then you would send that back to get your AX. Now, this is probably more steps than it takes than in terms of computations. This is really not that powerful of a theorem, but it's still good for us because we can see how this works with respect to transformation. So a good example probably would be a transformation that we're kind of familiar with. You guys remember the skewing transformation when we skew something, a horizontal skew? Yeah, some K. So let's see if we could do that, use that as an example. So our example is going to be, well, what's our example again? Now, 1, 1, K0, this is a skew example, right? So if we could also like stretch it horizontally by 2 and stretch it vertically by 3, and then do what do you call it? A skew by another number, a skew by 4. So let's see, since we're talking about transformations, let's see if we can get an easy visual out of this. First, we need to define a space here. Let's define a square. 0 less than x less than 1, 0 less than y less than. Okay. Something about defining a square. And then now let's transform this into that skew thing that we're talking about. Uh, 2, 4, 0, 3. Oops. Sorry. Prime. Prime. So it grew a little, it stretched by 2, it stretched by 2, and then this thing stretched by 3. If we look at the height of that transformed, come on. The height of that transformed figure is now 3, and then we skewed it by 4, so it got moved over by 4 units. Okay, so that's a fairly easy linear transformation that we've been dealing with. So that's a general picture of what's happening. So if we go ahead and compute the eigenvalues and eigenvectors, this is easy enough. It's a 2 by 2 matrix, right? So what's the eigenvalues? I think our lambda 1 is going to be 2 and our lambda 2 is going to be 3. So if we were to compute the eigenvalues, you'll see that 2 minus lambda, 3 minus lambda. Let's work it out here. And then the determinant of this is just 2 minus lambda, 3 minus lambda, minus 0. So it's just going to be 2 and 3. So now let's figure out the eigenvectors. So the E vectors would be, for lambda is equal to 2, we would put 2 in for lambda, 2 in for lambda, wait, 2 in for lambda. Oh, this is just 1. So this is just going to be, what's the free variable here? So 0, 1, 0, 0. Free variable is x2. And then x1 is going to be just equal to 0, right? Or anything. What? How does this work? Yeah. So x2 will have to be 0. So x1 is just, x1 is a free variable. So it's just 1, 0. So 1, 0 would be the eigenvalue for this. And then when lambda is equal to 3, we have 1, 4, 0, 0. And then here, this is free. And then x1 is negative 4x2. So we have negative 4 comma 1. So this is our eigen, this is our V1, this is our V2. So then our P matrix, if we go in this order, our P matrix is 1, 0, minus 4, 1. And then our D matrix is going to be 2, 0, 0, 3. So what that means is that, it's 2 o'clock, but what that means is that if we take any random x vector, if we take a random x vector and then we apply it to the inverse of this and then multiply it by d, then we would need to again multiply it by p to get it back to the original transformation. So I don't know if that helps, but try to think about that as a transformation. So I'll try to clean up this example in the beginning next time. I'll put up a review for our exam that's coming up. Yeah, that's coming up on Monday, and then we'll do more reviewing tomorrow or on Wednesday. All right.